Hey guys, so this video I'm going to show you how to plot the volatility smile, skew, or smirk with real market option data from interactive brokers with ib-insync. I'll define what this volatility smile or skew is in a few moments, but first, along the way to get this, we're going to show you how to get the options chain and also how to calculate implied volatility with one of interactive brokers methods and option price and also show you how to get Greeks. But before I discuss that and before I define the volatility smile and smirk, let me just remind you guys of what we talked about at the beginning of the last video, where for some reason the ib-insync library, the author's GitHub, everything has been turned to a archived, and this is a bit scary. Not because, of course, we'll lose the library. That's not a big deal, but like it's really scary because if you go to his name here, you see this. I don't even want to say it. It says dead, and then you see The Hague 2024. God forbid. I hope this is just a prank or something. God forbid. I hope this is just him not wanting to do this library. He's a really nice guy. I really hope he's okay. I pray he's okay. Obviously, this is 100 times more important than this library or anything. I just hope he's okay. If anyone has any information, please let me know. Also, the user group mysteriously vanished, but this was so sudden, like out of nowhere, this happened. So, like, I really hope he's okay, and it was just maybe him needing to take a break and get away for a bit. I pray that's the case. If you guys know more information, please let me know. So, like on that sour note, let's hope everything's okay. But let's start the video. Okay, so I'm going to show you how to get this volatility smile or smirk. What is a volatility smile or smirk? So basically, what happens is if you fix an option expiration date, um, you tend to notice, first of all, Black-Scholes model assumes constant volatility no matter the strike price, right? But in real life, you do not have constant volatility. You tend to see a few different types of patterns. One pattern could be that at the money options, like if the stock is at the strike price, have the lowest implied volatility, and in or out of the money, depending on call and puts, have a higher implied volatility. This could be the case. I think for some things it is the case. Um, and there's also like a volatility skew. So what's a volatility skew? The volatility skew is basically a phenomenon where often you see, especially for put options, you see that the strike price, the lower the strike price, meaning the put option is out of the money, has actually a higher implied volatility. So one way to think about this, one interpretation is um, that implied, the higher the volatility, and by the way, just as a reminder, implied volatility is basically a volatility you put into whatever option pricing formula. Um, you have an option pricing formula, and you have the market price of the option, and you solve for volatility, and that's implied volatility. Okay, so one interpretation behind why for lower strike prices, especially for put options, the implied volatility is higher is because there's more demand for out of the money puts. In other words, more demand for catastrophe insurance, for like a market crash or something. So that's why with more demand, it causes the option price to go higher. And of course, option price going higher with other things being fixed tends to solve for volatility. You get a higher volatility. So that's one interpretation: is supply and demand causing this applied volatility to be higher. But maybe for a smile also, you get a case where like on this side you have people with like FOMO and uh, people like don't want to miss out. Like options can be cheap, so that could bid up the price for these options on the higher side. One also thing to note is put call parity requires that if you have European options, we do not have European options. We have American options in America. But if you have European options, the put call parity requires that the implied volatility be the same for like the same strike for a call and a put. So like a $200 strike, the implied volatility needs to be the same for a call and put option. Otherwise, there's an arbitrage opportunity with put call parity, and we can talk about this in a different video. I don't want to lose track. So basically, to summarize, we're just going to show you with real market data how to maybe get one of these graphs, because like this is fancy in practice. In theory, you get these nice graphs, but in real life, data is messy. And a similar concept is you have the surface where you also have another dimension of expiration, and we'll make another video about that. But okay, let's get started with the code. Okay, so let's get started with the code. 1 second. Okay. 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 First of all, you need to import Plotly. I'm gonna make the plots in Plotly so we can zoom in. So the first line of code is just to make this window bigger. Let me just restart to show you guys. If you guys seen my other videos, you probably can guess this thing. So import. You make the import. You connect to interactive brokers to IB. You get the okay. So this is how you connect to IB, like on all my other videos. Okay. So first, what we need is we need to just for a given expiry get all the strikes of the options and get their market data so we can get these graphs. So first thing, let me remind you guys how to get the option chain. So you can use this ib.rec sec def opt params method to get the option chain for a specific stock. So let me show you guys how to use that. So first of all, you have this underlying stock, right? And you're gonna need to do ib.qualify contracts on the underlying stock because you're gonna need the con ID, the contract ID for that stock, the unique identifier of the stock. And this, once you have the underlying, then you can call this ib.rec sec def opt params method and to get the options chain. So what I did is I did options chain equals ib.rec sec def opt params underlying symbol equals underlying stock.symbol. This parameter is fut fop exchange. They just say leave it blank. I guess it's some internal use thing. I don't know why they keep that. Underlying security type will be underlying stock, that's sec type. Underlying con ID equals underlying stock.con ID, and that's why you needed the qualify contracts to get the con ID. So you run this thing, and you get a list of option chains, and it'll be one per exchange. So if you do length of this options chain thing, you'll see that it's 19. So you have 19 different option chain. But let's focus on exchange equals smart, and you'll only have one. So what does it have? It has the expirations. Here the expirations and has the strikes. Some of these strikes are not valid, but I guess it gives you like the full product of if at least one of these expirations has a strike, it'll give it here. But it could be that for this specific expiration, not all of these strikes are valid. This is just like the maximum product thing. Okay, and let me show you guys. Okay, so once you guys understand this, we can just have this method to get the option chain for a specific symbol. The input is symbol. Like here, you get the underlying stock with that symbol. You do qualify contracts, and then you get the chains by doing .sec type, .con ID. And then you're going to take just smart, and because the length is 1, you're going to do 0 here, you get the chain itself, right? Okay, so now this gives you the option chain. So let me show you guys how this works. Now if I do this, I get option chain Tesla. I don't know why I still play with Tesla, but anyways, you get the option chain here, and it's the same as here, except it's not a list, right? Okay. But for our specific example, we want options for a specific expiry date. And so let's say we want a specific expiry, and we also want to filter between a minimum strike and a maximum strike, right? We're going to also, I'm going to note is we're going to now get a list of options. Basically, for a specific expiration, we're going to have all these strikes, and then we're going to go one by one. So we're gonna go one by one and get a list of options contracts, And then we're going to do this ib.qualify contracts thing, and this will get rid of all the option contracts that are not valid, and it'll be left with just the ones that are valid. So let me show you guys how this works. Okay, so I guess I needed another import that I forgot. Import numpy as np. So now let's do this method called, I'll call it get options chain for expiry. So this will get the strikes for a given expiry date. So what it does, as I said before, is you call the previous method to get the option chain for smart, and then you have this options is just an empty list. You go through all the strikes. The strike has to be between the min and max strike you care about, and you go for writes, call and put. You create this option contract. You have a list of option contract, and then you run this thing. This is key. You do valid options equals ib.qualify contracts. You need to do the star because the star turns a list into basically a bunch of arguments. And what this will return is actually a list of option contracts that are valid. And that's why you'll see a bunch of red error things for the non-valid option contracts. So let's run this. Let's just for the sake of example, let's use Tesla. And let's do the contract for in 2 weeks from now, the 322. Let's do minimum strike 160, maximum strike 200. And as you see, I'm running this thing, and you'll see you'll get a bunch of no security definition, that sort of thing. But you're left with the ones that actually have contracts. So you get left with this. Okay. So now that we have this, let me just remind you guys. And of course, this is a repeat of my other video, but I figured. But I figured like it would be good to do this because I didn't put the other one on GitHub. But like, okay, basically, let's say first of all, let's get okay. So I have these valid options, right? And now let's get let me write this. Get market data for these valid options for the chosen expiry date. So I'm gonna create a dictionary with market data. I'm gonna call it tickers dict, and I'm gonna go through the valid options, and I'm gonna have the key being the write, meaning call or put, and the strike. So write, strike is the key, and each one I'm gonna request market data with the option contract. This thing is basically what we want to get, what ticker types we want to get. This is like the default. And then false means we don't want just a snapshot. We want the data to keep updating. If you have true, you just have it one time. And maybe I'll just write the arguments to help you guys out a bit. Contract equals this. Equals this. Generic tick type list equals that, the default. And then snapshot equals false, because if it's just a snapshot, it doesn't update the data. And there's a thing called regulatory snapshot, and let's do that false. That's something you have to pay, and you get like the NBBO National Best Bid Offer snapshot thing. Anyway, so I did this market data. Maybe you should do like an ib.sleep 2 or 3 to make sure that it got filled. And let me just show you guys how it works. It looks like a dictionary with each one being like the ticker. And just for the sake of an example, let's take the 180 strike call. And let me remind you guys on a few different things that option tickers have with interactive brokers. So they have model Greeks, last Greeks, bid Greeks, and ask Greeks methods that give you like a lot of the information. So model Greeks, first of all, just real quick for a second, is that there's this thing called ticker.midpoint, and this gives you the midpoint right now of this option, right? So you can do ticker.midpoint, and you get the midpoint of this option, right? But you also have these things called model Greeks, last Greeks, bid Greeks, ask Greeks, and they're going to give you like the Greeks and implied volatility and option pricing depending on model means IBKR model based. Last means the last price traded. Bid means based on the bid of the option, and ask is based on the ask of the option. So sometimes the bid and ask ones make no sense, and the last one makes no sense just because like there's no volume or it's way out of it. But I picked a reasonable range of strikes, so like it should be okay. The model based one always kind of is nicely behaved because it's their model. It's their model. But anyways, let me just show you guys how this works. So you can have so like the model Greeks, you have ticker dot model Greeks, and if you click this, you see you have the option price, you have the delta, the implied vol, gamma, all the other Greeks, but you have also like the underlying price, 176.37, and you have the option price. But let me just show you guys for a second that like the option price is different than if you do like let's do just ticker dot midpoint and let's do ticker dot market price just for sake of trying. So you see that okay, by luck it happened to be that but okay, it's not necessarily the same. As here you see option price is not the same as midpoint and market price necessarily because this is based on their model. And I'll go back to that later. Last Greeks is based on the last traded price. So you can do ticker dot last Greeks. And this would correspond to ticker dot last. So as you see, ticker dot last Greeks, you have all the Greeks based on the last traded price, the implied vol, and the option price. So the option price is 5.45, and as you see, this is 5.45 because of all the rounding. So that makes sense. And of course, you have the implied vol and all that stuff. Now there's ask Greeks, very similar, except this is ask Greeks. It's based on the ask price of the option. Note for the underlying, it's going to use it's going to still use the last price, but for the option, it's going to use the ask. Okay, so like if I do ask, I'm going to see I get 5.55 is the price and 5.55, and then bid Greeks, I'm going to get very similar thing, but based on the bid. Okay, so this is just a reminder of these things. So also, Interactive Brokers has a few options-related methods. There's a thing called Calculate Implied Volatility, which allows you to calculate the implied volatility. There's ib.calculate option price, which allows you to calculate the option price. So let me just demonstrate for a second how these are used. And the reason I want to talk about them is later we're going to actually use this calculate implied volatility because there is no such thing as ticker dot midpoint Greeks or something. By the way, there is a ticker dot. Is there a ticker dot implied volatility? I always get nan for this. Maybe you guys know better than me. Anyways, but because there's no midpoint Greeks, and as you'll see, the bid and ask Greeks are a bit weird, we want to be able to calculate the implied volatility on the midpoint because the model Greeks, you'll see in a second, are based on on European options, and that isn't really the case in reality. We have American options, and so I think it is good to see it. So let me just illustrate how to use these two methods for a second. So first of all, there is this ib.calculate implied volatility. You have to give it a contract. So ticker. So let me just write everything. Contract equals. Let me define it here. Actually, I'll do contract equals ticker dot contract, and then contract equals contract, and then what else do we need? We need option price equals option. Let's just do it like this equals ticker. Let's just use the model Greeks option price. Let's do the midpoint. Midpoint option price, and then the underlying price we can do ticker dot model Greeks dot und price. That gives you an underlying price. So like option price can be option price, and then und price can be under price. And then as you see, it gives you this computation thing, and it gives you like the gives you the implied volatility here. 0.48 whatever. And just for the sake of example, I could do something like I can get the implied vol, and let me just see. Sorry, okay, I could get the implied vol. Okay, um, and if I were to have done something like this, let's just see that this makes a little bit of sense. Let's just assume I were to use like model Greeks dot opt price, and then I'm gonna do print model Greeks implied vol ticker dot dot model Greeks dot implied vol. You see that the implied volatility is really close to the same thing. So that is basically, this is a way to calculate implied volatility. Um, you could also change the option price to whatever you want and the underlying price to whatever you want, and it'll give you a different implied volatility. But anyways, I don't want to talk too much about this. Now there's like this calculate option price method, which calculates the option price. So let's show you the example. ib.calc option price. Oh, and there's like the async versions, and I'll show you guys because like if you do like some sort of event loop, like let's say like on bar update, and you're using this, you can't. You need to use the async one. So I'll show you in another video how to do that. But let's do a similar thing where we have now we calculate the option price. We have the contract, the option price, the underlying price, right? So as you see, it takes contract, and it takes here it doesn't take it takes volatility. So let's do volatility equals ticker dot model Greeks dot implied vol. So we'll do contract equals contract, and we'll do volatility equals volatility. And then we're going to do underprice equals underprice. So like basically you get the calculate option price. But what's interesting here is so you also get some Greeks for free and stuff like that. But what's cool here is like, okay, so this is like the I'll say this is a current. I'll do this. Okay, sorry. Let me just copy and paste this, and I'll do something like this. I'll do this like current option price, and this is not correct. This doesn't take into account time value of money, theta, and that sort of thing. But just like as a rough estimate, I can do something like this. I'll say option price if stock goes up $5. So I can do something like ib.calculate option price, and now I'm gonna just give it under price plus 5, and then let's call this current option price, and then I'll take out the opt price thing, and then you can print it. You can do like current option price up price if stock goes up $5, and you see if the stock goes up $5, the option will go up almost $3. So that is interesting to see. Okay, so now let's get to the, oh sorry, this is the recording thing. So now let's get to the actual volatility smile, smirk, and skew graphs. Okay, so the input is going to be a data frame. I want to create, first of all, a method to plot these graphs. So this method is going to basically use Plotly Express, and it's going to, let me write Plotly Express graph. The Plotly Express takes a data frame, and then you'd have like an X value and a Y value, and it plots X versus Y, and then you can have the color based on a group. So let me just show you guys. So let's create a method and assume you have an input of a data frame with strikes and implied volatilities. And then this method will just graph it. So it's something like this. I mean, this is not like a video on Plotly, so I don't want to get into too much detail, but like this will be your data frame. And then maybe 1 second, maybe I'll just write data, what's it called, data frame equals this. do x equals that, y equals that, color equals right, and fig that show. So basically, we'll plot strike versus implied vol, and it'll have two curves, one for call and one for put. So first, let's show you guys how you can let's get this curve for model-based graph. So because European, you'll see that there's actually only one curve in this case, which means that basically that the for every stock price, the implied vol is the same, no matter call or put. It means their interactive is using a European option. So first step is to create this like implied volatility data frame. So you do implied vol df equals, and then what I'm going to do is I'm going to take from this dictionary, I'm going to iterate over it. I'm going to get the right, the strike, and the ticker. And basically for this one, because it's model based, I'm going to do model Greeks that implied vol, and then right and strike, and then give it columns right, strike, and implied vol. So it's going to look like implied vol df like this. It's going to have this implied vol df. And now to plot it, I'm going to do, of course, plot implied vol df. As you see, it's one graph for both call and put, the exact same thing, because they're using a European formula. Okay, so now let's do a similar thing for like a last base graph. And this one, as I wrote here, is a bit messy because some things don't even have trades at all, and some things don't have recent trades, so it's going to be a mess. So if I do last Greeks here, the only difference is I change this to last Greeks. I plot this. Wow, that's really bad. Yeah, it's ugly just because it's real. It's based on the last thing, and some don't have things. So a little bit more reasonable is the bid based one, because but this is based on the bid, and with options sometimes the bid and ask have a huge difference. So midpoint is often better. So you do this bid Greeks, and then you see here in this case bid is like in this case the put option is more expensive because bid is the lower of the price. I don't want to get into too much detail because I'm all over the place, but this is a bit messy. Here you're going to see that the put is more expensive at the lower strikes than the call. And at the higher strikes, the call is more expensive than the put. But if you do ask, because bid, it gives you the lower price, right? So when the price of the when the price is lower, it implies the put option's volatility is more, and the call is less. I'm losing my train of thought. I don't want to get into too much detail. This is just showing you guys like the techniques. But ask based graph is similar, except now we're going to do ask Greeks. And sorry if I didn't make any sense, but okay. So ask Greeks, like I said, it's the opposite thing, where the calls is more expensive and the puts is less. But we really maybe want a midpoint based Greeks. But this we're gonna have to do some work because there's no such thing as like ticker.midpoint Greeks. So here, instead of doing just ticker.ask Greeks.implied vol, we're gonna have to create our own method to compute implied vol. So let's do that using the calculate implied volatility method above. And by the way, this is where maybe in the future it's better to use a different library, like maybe QuantLib or whatever, for implied vol to get like more sophisticated stuff. But anyways, just for now, let's use interactive sing. So it's just a function where like you input an option ticker and you get the contract from it. When you do dot contract, you get the option price by doing option ticker dot midpoint. Here I printed it out just to give myself some debugging. Underlying price, to get option ticker that last Greeks that unprice. You can also do model Greeks that unprice. Unprice, from my experience, is the same. This is the underlying price. And then we're going to calculate this implied volatility model with option price, underlying price, and option contract here, similar to what we showed you above. And then if it's none, we're going to return -1. If it's valid, we're going to return the implied volatility. Sometimes you get numerical things that make it not work, and you'll have this -1 thing, and then we'll filter that out in our graph. So we can get the implied volatility data frame. This is not instantaneous like the other one, of course. But you're gonna similar. We're gonna iterate over the tickers dict. We're gonna get the right, the strike, and then we're gonna call this method on ticker to get the implied vol, and then we're gonna get this like implied vol df. And you know what? I'll print it on the next line. So you see, I printed all this junk. So now I have this implied vol df, and I have a right call, strike, implied vol. And now let's plot this thing. So we can plot it using our usual method. And here it's, it's so funny. I ran this like before to practice this video, and the opposite conclusion happened. Did I mess up here? Maybe implied vol df. I don't think I messed up. Anyways, it's really weird. Here you see that it's actually that the call options volatility is more expensive here, and the puts is more expensive here, which is weird. I guess I don't know. It's hard to interpret. You probably need a bigger data set for this. But let's do a different example. This is okay. This is some random Tesla example. Not that many volatilities. Let's just do like a actual like real example, and let's do like a later strike. Okay, so let's do a later expiration. So let's do something like we picked Tesla here, but why don't we do something like why don't we do instead? Why don't we try like Nvidia and first of all, this okay. So I did this for Tesla, but let's also add for Nvidia and just see like what you know what. I don't need that because I only need is the expiry. So why don't we choose the first expiry in January that we have of next year? So I think this is January 2005 117, and this is let's see how this thing looks. It's interesting actually. So we are going to now do NVIDIA. Of course, we're going to have to change the strike range a lot. So let's do minimum strike. Let's say NVIDIA's, wow, NVIDIA's a lot today. NVIDIA stock price. NVIDIA is 915. Damn, that's crazy. Tesla is, ooh, surprised. Maybe it's because Rivian has like releasing a new car, so maybe it's not struggling that much. Anyways, so if Nvidia is around 900, maybe we'll make the range between 600 and let's do 1200. Okay, so now let's get this valid options for Nvidia for this range, and let's see how this looks. So now valid options is this thing. So let's get the market data for this. Let's wait for it to fill. We get the dict. This is not going to work anymore just because this is based on NVIDIA. So let me just, because I'm going to put it on GitHub, I'll do, I'll clear output for this example. Oh, you know what? Let's make it work. So I'll do, so let's do like 900. That'll work. Okay, so we get 900. So that's a very expensive option. Okay, so like similar methods we did below, but now let's do the smirk smile graphs. So this is the model based, which is like it's interesting here because this is kind of showing that options might be pricing more risk for it to go down. There's more demand for it to go down. Last base is based on the last price. This is going to just be a mess because there's not enough data. Bid based, again, similar. This is higher. Ask based. And let's do the model based. By the way, this is like a completely raw, unfiltered video. I had this video prepared a few months ago, but I never got around to doing that. Oh, this is messed up completely. Oh, because I have this -1 stuff, so I need the to do like dot query imply query is a way to filter vol greater than 0. Oh, okay, so it's interesting. Either way, like this is a super skew, and the call is more expensive than the put. Maybe this is like a FOMO thing, because like I read on a lot of books and stuff that usually the opposite case. But anyways, this is just kind of showing you guys some things. I don't know if it's practical to real trading. A lot of people actually trade volatility, so it might be. But like, if you enjoyed this video, like, I didn't give my plugin today, so like, please like and subscribe if you learned something. I appreciate that. It makes me smile a lot. I'm almost at 500. Some of my friends like think 420 is a bigger number, but I don't. But anyways, I really appreciate it if you guys like and subscribe. And on a more serious note, of course, if you guys know what's going on with the author of ib-insync, what's going on with that, please let me know. Hope he's okay, and I hope you enjoyed this video. Thank you guys so much. See you next time.